Okay, so the first thing, that we have to kind of address before we get started though with Kangaroo is that Kangaroo, like a lot of the plugins that are made for Grasshopper, right, is primarily made for mesh geometry, right? So you're not going to really see a lot of, surface NURBS and those kind of tools being used. Now, so I think it's important that we spend a little time to be very clear about what the differences are, right? So, in our time working with Grasshopper up until now, we've used kind of a lot of the different components in all of these tabs, right? But the one that we kind of avoided and we didn't use all that much was this mesh tab, right? And to be honest, there are not that many mesh tools, right? You can see there's a few mesh analysis tools, a few mesh utility tools, and then primitives to help you construct basic meshes, right? And then some, seemingly random mesh exercises, right? The reason for this is simply because mesh geometry is in a way the most primitive type of 3D geometry that was available, right? It was one of the first types of 3D modeling methods that was developed, and it was very simple, right? You defined 3 points in space and you can make a triangle, right? And you put the triangles together and they form a bigger shape, right? And that's pretty much as complex as meshes got, right? So it's drastically different in terms of what mesh, the amount of the processing that's required to work with meshes than, for instance, with a NURB surface, right? So a NURB surface is very complex because, again, we're dealing with complex calculations to define curvature, right? And that curvature, was set to several degrees, which meant, like, if you had set it to 6 degrees or 8 degrees or 11 degrees, at every point you created, right, was affecting, its 11 nearest neighbors, right? And so those calculations, obviously make the geometry much, much heavier. So what is then the advantage of working with a mesh, and what is the advantage of working with a NURBS geometry? Well, again, if you think about it, working with NURBS geometry, we could create nice curvature and we can do nice blends, right? And we're interacting on a kind of higher level, right? Where you're lofting lines together or blending one edge to another edge, right? But we're not really having to do any of the kind of mathematics and calculations, right, to make that happen. That's all happening on the side of the computer. With mesh geometry, the computer is hardly having to do anything, right? And we're defining every single point that we're, and we're moving a point or modifying a point, and all it's doing is, connecting those 3 points and making triangles for us, right? But you can imagine that as soon as a geometry gets bigger, right? Or if you wanted, for instance, you wanted to draw a curved surface, but you didn't want it to look like a faceted triangle, right? You want it to actually look smooth, right? That means you're having to adjust thousands of meshes all by hand manually, right? And so you can see that it made sense at a certain point for people to move away from meshes, right? Because it just became too tedious when you're trying to develop highly detailed models, right? But it's also very appealing for programmers because of its simplicity and because how light it is, right? Again, it doesn't require a lot of processing. And what you'll see is that when we're working today, a lot of what we will be doing is going to be primarily mesh-based. And in order for us to be able to control those meshes, we're going to rely, right, on some exterior factors, right, to control the shape that we're looking for. And so let's go ahead and do a quick example, though, just so that you guys can see visually the kind of differences that I've been describing to you, right? So let's go ahead and start with comparing a couple of things. Let's compare a sphere that we've generated using a NURB surface, right? So if you remember from Rhino, right, a sphere is more or less a four-sided sheet that's kind of wrapped up on itself, right? So if we tell it to, okay, visualize the UV curves on that sphere, right? So we go to our analysis, we choose our rep edges component, right? And you can see that if we wanted to visualize this, right, there's no additional information required in order to define that sphere, right? Now, if we compare that to, say, a sphere primitive made out of a mesh, right? And let's just use the same. However, I'm going to move it to the side so we can see them side by side. Let's choose a direction, say X. Right, so if we compare these two spheres, one is a NURB sphere and one is a mesh sphere, you can see already that the NURB sphere is very smooth, right? Whereas the mesh sphere has this kind of faceted sides. And if we want to visualize, we can go to our mesh tab and we can tell it to turn on our face boundaries just so that we can look. And you can see that, you know, this sphere is comprised of a mesh with this many faces, right? And that's why there's that faceted appearance, right? Now we could, you know, try to make it smooth, right? But with mesh geometry, the only way to do that would be to increase the count, right? So if I change my U count and my V count to, you know, something very low, you can see that it becomes blockier and blockier, right? And if I change it to something very high, then it gets, you know, closer and closer to what we would call a perfect sphere, right? Which is this one here on the left that's defined mathematically using NURBS geometry, right? No matter what you do with the mesh, right, there's always going to be some amount of error and tolerance, right? Because, you know, if you zoom in, even divided, if something that's divided by 100 times will have facets, right? And won't be completely smooth. So the basics is that you can imagine now if I wanted to modify this geometry, right? I could do that by hand very easily, right? If I wanted to modify this mesh sphere, right, it becomes very challenging because look at how many points I'm working with now, right? So it becomes very difficult for us to work with at that level, right? Okay, so that said, however, we're going to be using mesh geometry today with the Kangaroo plugin because the simplicity of the geometry itself allows us to not have to deal with, makes programming, I guess, for Kangaroo simulations much easier, right? Because there'll all be approximations of what we're working on, but it's far more practical because it requires much less computational power, and if we needed more, then it simply would have been, you know, too heavy and too slow. So let's try our first example, and I think the first example that we'll look at will be the hanging chain, right? Okay, so with the hanging chain example, we're looking at how to simulate methods, real methods that, Antonio Gaudi used to develop the form for his project, right? So we talk about this as we use the term form finding in architecture to describe a way of generating form, right? That's dependent on kind of external factors that are not necessarily within the architect's control, right? So in this case, we're using the force of gravity, right? And taking advantage of its effects on a chain, right? To generate that kind of curved arch-shaped parabola, right? That forms the basis of the design, right? So to start with, we want to set up our definition, right? So that all the basic components are there. We're not thinking at all at this point about the fact that, it needs to create this kind of arch or a U shape or anything. That's not important to us at all. We just need that all the elements, right, of our design are there, right? So to do that, we're going to start with a line. And we're going to go back to our curves. We're going to say, let's start with SDL line, right? We'll accept the default XY axis as our starting position. We can choose a direction for how that line extends out. I'm going to choose to do it in the X direction, right? And then I'm going to give it a length. I'll just do something random for now, 100. So this didn't have a default, so I'm going to go ahead and set a XY. There. So you can see that we just drew a line basically from here to there, right? Now, again, just like in previous examples, we're only using this line, right, as a way to generate our chain link, right? And so what we want to do is we want to go to curve and we want to divide, right? And we're going to divide our line into segments, right? At this point, we can choose as many segments or as few segments as we want, but I'm going to go ahead and use 100 and then pull that 100 slider and then reduce that to something that looks reasonable, 20, let's say. All right, so there's our 20 points on that line. And then we're going to draw a curve with a polyline through those points, right? So that, we started with this, which was just a line segment, a single line segment, and now we've converted basically that line segment into a polyline, right? And the reason that we did that, though, is because we're going to take this and then we're actually going to explode it using our utility explode into segments, right? So line-like curve. And you can see there's 21 line-like curves because when we built that polyline, we built it with 21 points, right? So now we have 21 segments, right? Which makes, simulates the elements in our chain link, right? As if each segment was one link in the chain, right? So believe it or not, that's all there is for the geometry, right? The setup part of it. Now, the second part of the setup for all kind of, kangaroo physics simulation types of definitions, right, is that you have to create the environment too, right? So now we set up the system, right? The physical object. We also need to set up the environment. And to do that, we have to consider a few things, right? So we have to consider first, what loads are exerted on that chain, right? And in this case, we're going to add a load, right? And this load is going to represent the load that it's going to represent the load on our environment, which is gravity, right? And it has a direction to it. So in this case, you can see we have a force vector, right? And that will define the direction. You can see by default, it's set to 1, right? But I think what we want to do is to be able to modify that. And I think it makes more sense to use a negative direction. So we're going to say Z is our force vector direction, and it needs a value. So we'll use a slider, and it needs a mathematical direction change, right? So we'll go to our operators and say negative. So now our force, right, is negative, and therefore can simulate the effects of gravity, right? And we still need the points in which that will be affected on, right? And the points are going to be at the end of those segments that we just created, right? Which are the same, right, as our divided points here, since those are what we use to generate the segments. Weighting, again, if you read the description, it says you can often leave this at its default of 1. And the reason for that is because weighting is really something that's used to control your environment when you have more than one force, right? So let's say you had multiple forces, you had wind and you had gravity and you had whatever, right? Then you can modify, the amount of contribution by each force by changing its weighting in the system. For us, since we're only using this one force alone, I don't think it's particularly important, right? So we're just going to leave it the way it is. Now, okay, so let's see what happens if we were to just keep this geometry and this force and run the simulation. So to run the simulation, what you need is you need to go under Kangaroo 2 and you need to find your solver, right? And there are a number of different solvers. The basic one is just called solver, but they have things like a bouncy solver, hard and soft solver, step solver, and it just changes the way that the visualization, right, of the calculation when it occurs, right? You guys can play with that on your own. They basically have the same, kind of inputs and outputs. It just changes the effect of what it looks like when it's doing the calculation, right? Okay, but so we're going to connect everything to our goal objects, right? That includes not only our environmental forces, but also the geometry that we're working with. The only thing is that we need to use a show here, excuse me, on any geometry that we put into our solver, right? That will let the solver know what things we want it to show during the calculation. Then unitary forces is our gravity force, right? So we'll also connect that, remembering to hold shift, right? And you'll also see that we have two things here. We have a reset and a on and off, right? So I want to create two buttons, right? One toggle button, right, to turn it on and off with a Boolean, true and false, and one regular button that just activates when you push it, right? So I can use that for the reset. So at this point, you can see that when I connected the Boolean toggle to on and it's set to false, it says pause, right? And as soon as I turn it true, right, it changes to running. Now, we're missing something here still, and I'm going to hide all of this first. What we're missing is something to hold the geometry in place, right? So far we've only set up some things that will exert a force on it, but we don't have anything to actually hold the geometry in place. So to do that, we need to go to our Kangaroo tab and we need to find, say, an anchor, right? And an anchor is simply a way of defining a position or a point on our line, right? Where we don't want anything any of the forces to affect, right? So it'll basically be like something that holds it in place, right? So to do that, we're also going to extract 2 points, right, from our original line. We could, of course, also take our points from here, right? But let's say if we just took our points from there, what would happen is that all the points would get locked in place, right? So we could either use line index, right, from our set to pick the points that we want, or we could use, like in this example, let's do the end points of this line, right? And let those serve as the anchor points, right? And so what happened? You can see that here, those 2 points didn't move, and there's a line that's getting stretched out to infinity, basically, right? Because all of those that had this force exerted on it, just fell, right? Reset. So all those points between the two ends fell to infinity at a certain speed that we set, and we only saw the 2 points that got held in place, right? And were left behind. Now, that's because we didn't define the physical characteristics of this line segment, right? So because we didn't define that, it assumed that that line segment was infinitely stretchable, right? It had no physical properties to it, right? All it was something that was connecting those 2 points together, right? So what we need to do is we need to define the characteristics of that segment, right? So we got to go to our Kangaroo, and we know that's a line geometry. So we're going to go to our goals and line, right? And we're going to pick one of these characteristics, right? In this case, let's use the line length, which is also a spring force, right? So this will allow us to define that segment of string, right, in terms of how stretchy it is, basically, right? And so we can say, okay, have 2 sliders, one that controls the length, one that controls the strength of the line segment or chain segment, and then those segments will be input as well, right? And from here, right, we're just going to add that by holding shift again to our goal objects, right? So we reset it and then trial again. You can see that now it isn't falling to infinity anymore, right? It's falling to a certain length, 100, right, before it reaches its maximum and then gives up, right? So eventually you can see that, oh, so it's fallen all the way down and then comes all the way up, right? If you change the length now, right, you can see that I'm affecting the maximum length at which that curve can transform, right? You could also do the opposite, which is change the strength of the material as well. And by changing that strength, what you're effectively doing is you're changing you can see the proportions here. The distance of this stretch is much longer, for instance, than the distance of these stretches, right? And as you lower that strength level, they all become kind of an evened out, right? So in our example, I think what we want to do is we want to be able to, if we were doing a simulation of a chain, right, where each link stays the same length, right, and you just define the length and, you know, let it do its thing to figure out what the form or shape will be, then that makes a lot of sense, right? If our model was made out of rubber bands, right, which do have some elasticity to it, then this strength factor probably needs to be modified a bit, right? Because you would expect, right, the ones that are under greater load will extend more than the ones, you know, kind of down at the bottom and middle section, right? So that's how you would use the strength characteristic to define that geometry, right? And you can see now, you know, we set 2 anchor points, but if I now changed and I said, okay, I'm going to remove one of those anchor points, then do the simulation again, and that just dropped that side down to here, right? So you can see that that's a very easy way. And if we were just, you know, if you just imagine, instead of drawing, you know, a single line, I input, you know, tons of lines from my drawing and did run a simulation of that, you know, we would get something very similar to what you see here, right, in these examples. Okay, so why don't you guys give this example a try? I think it's a good way to start exploring the kangaroo and physics simulation, because you will have a chance to understand, for instance, the concept of working with different forces and how to combine them and how they work together, as well as, you know, how to set up a scene or object, right, with all the important characteristics that need to be built in order to run a proper simulation and determine, you know, the end shape, right? Okay, try that, and then we'll come back and work on the next example. Okay, so in the next example, let's see, we're going to look at working with tensile structures, right? So, or soap bubble type structure, probably tensile structures, I think, in this one. And you can see examples of this in, for instance, Frey Otto's work, specifically projects like this, right? And, you know, these are typically something that's very difficult to kind of predict in terms of what the final form is, right? And, you know, how to decide, for instance, in this example, how you would go about determining the panels, right, that you need to prepare in order to create this overall shape and form, right? And so it's very helpful to be able to simulate first in your 3D model, right? And then use the 3D model to determine all of that for manufacturing and fabrication later on, right? So if we look, actually, the strategy is not so dissimilar to what we were just doing, right? Except now we're going to be working with geometry that's not just line-based, but actually a surface-based. So actually I misspoke. It's not surface based, but it's mesh based, right? So let's first create our mesh, and I'm going to let's use our mesh primitive and plane, right, to generate our starting mesh. Now, I think we can go with, something with a higher mesh face count. And we can't see that, so let's go ahead and use our edge. We probably don't need 100 right off the bat. Let's shrink that down a bit. Let's do something like this to start with. Looks good. Yeah, so that's our starting mesh, right? Now, with every kangaroo definition, you already know that we're going to need, right, forces, right? And in this case, our force is, we still have our unary force. Maybe, I think, let's wait on unary force. Let's go to our, because we're working with a mesh this time, so let's go with our edge lengths, right, which is similar to our spring force, except that it works with mesh geometry, right? So we can straight away link our mesh to that mesh force, right? And then you can see here there's a length factor and a strength, very similar to what we had here with our spring force, right? So I'm going to use our slider, to control these, and I'm going to set them at a pretty low, something lower for now. And then we'll see, how we want to adjust them later on to create the effect that we're looking for, right? And as before, we still need anchor points, right? Because we want to define certain parts of our geometry that we don't want to move when we do the simulation, right? So anchor points will be under goals and points. So we come here to anchors, right? And we need to find those points that we're interested in. And I think the one that makes the most sense to me, right, is going to be those corner points, right? So you can see that with our mesh edges tool, it allows us to identify different edges of our geometry, right? If in this example, we're only interested in the edge boundary, not in all of these interior edges, right? Then we can choose naked edges, right? And do evaluation, our discontinuity on the naked edges. And you can see it will give us a set of edges, right? Now, I think this is not exactly what I want, because ideally I would only have the 4 corners, right? And it's also giving me the interior corners as well. So I'm going to take these these naked edges, I'm going to join them together to create a curve first, and then from there do the analysis for discontinuity, and you can see now it's only returning those 4 corners to me, right? With those 4 corners, I can define my anchor points, right? I could just throw them in there, right? And let's see what happens if I do that. I just throw them in there as my anchor points and use my kangaroo 2 with the solver. and the geometry, identify the geometry that I want to show, which is this mesh, right? And I connect that all up as I did before. And it's already doing something because I didn't have these yet. Button for the reset. Okay, so I reset it. I'm going to hide some of this first. So we're just looking at the solution, then run. And here you can see it looked like it exploded, right? Not really the effect that we're looking for. And the reason for that is because our length factor, right, turned out to be too high, right? And if we shrink it down, you can see that as we brought it, reduced our target length, right, you can see that now it became like a shrunken, slightly shrunken object, right? So you can play around with that a little bit, which indicates to me, though, that actually the range on our slider here is probably wrong. And let's use a slider with a range of 0 to 1 for our length factor. And that seems to give us, better control, right, of what we're looking for. Now, the strength, I don't think it's going to have any effect at this point. So let's just see. Yeah, not really as obvious in this case, the effect of the strength as we saw in the previous example, but it should still be there. So I'm going to leave something connected to it. So you can see already that as we added this kind of spring force to it, right, the geometry, and we only tied down those four corners, right, the geometry wants to kind of shrink and pull itself back in, right? And that's the behavior that we actually are expecting, right? Now, this is not as interesting, though, because, it's a kind of stagnant example. So let's say we want to be able to control these 4 points, right? Rather than just lock them down completely. So what can we do? We can pull this out a little bit and add an element here that'll allow us to manipulate those points. So the first thing I want to do is I want to separate out those points, right? And I'm going to go to our list item, right? Input that here, and I know there's 4 items because there's 4 corners. So I'm going to just go ahead and go 1, 2, 3, 4. So now I know this, one of these is 1, one of these is 2, one of these is 3, and one of these is 4, etc. And then I'm going to use a move command, right? So that I can move them around. And I'm just going to use the same move command for each of them. So let's say move, it's going to be like this, right? And that's going to be 1 point there, right? And you can see that that move moves it up. By default, it moved up 10, right? Let's change that so that it's a slider that we can control. We need to define the direction. So let's say Z. So a factor of 10 and then a motion Z. We probably need a little bit more space here. We set it up like this, right? And let's go ahead and Okay, so here we have on our anchor a point and a target, right? So the original point remains here, and the target is the location where we want to manipulate that point to, right? So you can see in this example, I created another point here out in space. You can see it moving now, right? And I told it that that was the target, right, of of uh, our solver, right? This point in space. So what it's doing now is that it's taking all the points that we're throwing into it, right? Those four corners, right? And pulling it towards this target, right? So when I activate the solver, you see all those points got pulled to that target, and then all the stuff in between just got bunched up here, right? Now, if I copy and paste this though, 4 times, once, for each of the four corners of our mesh, right? So we have one there, one there, one there, and then one here, right? And I use in the same order them as our targets. Now, when we activate, you can see it jumps from down here up to here, right? Not so interesting, but what that allows us to do then is to move these points in between, right? And it will solve for that transition within that shape, right? So now to get a little bit closer to our example, if we're looking at this kind of example, and we imagine that, okay, there's one patch here, we can control four corners, but we also want to be able to control kind of one, let's say one point somewhere in the middle, right? So let's break that out and we'll define another anchor point with another list item. This one I think goes this way. But then the target needs to be manipulated. What is the target here? It goes to let's say copy this. And the geometry is also this point. Okay. Let me change this range to something a little bit larger. Okay, so this index will be the number on our mesh list, right? Which will be basically, you know, if we look at this now, it has 81, so 9 times 9, right? So this one squared, do we have a square in our, to the power, the exponent to be raised 9, 2, raised to the 2, 81. That just gives me my range. We won't do that. We'll just define a value for now. So we'll use the index here for this list. That'll allow us to pick a point. But this list should not be from our discontinuity list. It should be from our mesh naked edges, interior edges, mesh. Let's see what analysis tools we have. Deconstruct mesh. So we take that mesh, deconstruct it, use its vertices as our list. And yeah, so now we can see that I can pick, different points on our original geometry and use that as a target as well. And by doing so, you can see now here, if I had selected, say, 0.55, right? I can move that, up or down, right? And run the simulation to ask it to describe that form, basically, right? And in that way, we're able to simulate something, fairly similar to this geometry, right? The only difference here is that maybe you have, instead of 9 by 9, right, you increase this to something much larger, right? And you add more edge points to serve as your edge anchors, and you add more points in the middle, right? So that you can have multiple towers, right, inside your overall mesh, right? And when you run the simulation, it should find, that the shape or outcome that you're of, what happens if you anchor those points and you push those points up, etc., right? So again, this is how you could go about finding the overall form based on certain characteristics, right, that you input using things like edge lengths for spring, as well as defining anchor points, right? So maybe you guys try this one as well. Again, I think it's not too dissimilar from our previous example, only now you're working primarily with not just the line or an edge, but with the entire mesh geometry itself, right? Okay, so when you guys are done with that, we'll move on to the next example. Okay, so in our last example, we'll be looking at minimal surface geometry. So minimal surface geometry, essentially what it's trying to do is trying to find the least amount of material needed to connect one boundary edge to another boundary edge, right? So a lot of these examples that you see, particularly, in the work from Zaha Hadid, right, is that, it's negotiating this one edge boundary to another edge boundary, and then trying to figure out, how to connect those edge boundaries using the least amount of material, right? This is also derived from physics study that Frey Otto also worked on, which is this kind of soap film example, right? Where, in a way like soap bubble and soap film, when you have kind of these edge conditions, and then the soapy water kind of creates this form or shape that connects it all together on its own, right? And that's essentially what the exploration of minimal surface is. And the application in architecture, I think, early on was particularly well developed, I guess, in a lot of these kind of pavilion-like scenarios by Zaha's office. So, it's not so different, in fact, from our previous example. However, we will need to start with some geometry that's a bit more complex than what we really want to generate here within Grasshopper, because the tools are so primitive, right? So what we're going to do instead is we're going to go ahead and use Rhino geometry and convert that, build the geometry first in Rhino and convert that into a mesh geometry, right? And so in this example, I'm just going to, quickly copy geometry. That's probably enough for this example, right? Join them all together, explode it into surfaces, and I want to open up these ends, right? Because we need some open edges. So I'm going to just take all those sides, open them up, right? And then join them together again, right? So I'm going to bring these into our Grasshopper canvas as a set of surfaces. I don't know. Yeah, okay, so I need to explode that actually. Just select all of them and set multiple surfaces. I'm going to hide the original geometry. And so you can see that this is what we've brought in. Now, we're going to go ahead and use our mesh convert, right, to convert our mesh surface into mesh geometry, right? You could also, you may also be able to use the mesh brep, but the reason I choose a mesh surface is because with surface, I have the ability to control the UV count subdivision, right, which is very straightforward and easy, whereas with the mesh brep, you don't have that option, right? So I just think this is probably the best way to go for this example, right? Then I'm going to use a slider to control that UV count like we were just talking about. And what that's doing is, if we visualize that using our edge component, it's subdividing our meshes into different densities, right? For the purposes of the model, I'm going to use the minimum that I need, I think, to get the form, and then we can play around with higher densities. But this will keep the model light and more workable, right? Now, from there, because one of the things that we know is that because we brought it in as surfaces, converted it, we have a lot of meshes, right? And they're all separate. So you can see there's 26 local meshes here. And what we want to do is we want to merge them all together into a single mesh so that, we can continue down the workflow without running into additional problems, right? So we can use a combine and clean under the mesh tools provided by Grasshopper 2, right? And that will combine those meshes into a single mesh, and also get rid of any potential overlapping geometry, right? So, okay. So just like in our other example, we're going to be doing a mesh and edge lengths, right? And that means we also need to find, well, we can just connect that right away. We also need our solver, and our solver will take as one of its goals that spring force. We also need to reset button and a on and off. So we'll go back to our inputs, choose an on and off, as well as a reset button. we need to tell it what geometry is important for us in terms of our visualization as before. So we'll use our show to let Grasshopper know. Let's connect shift that this is the mesh that's of interest to us. And we'll also need to define our anchor points, right? So the anchor points in this model are these points here that are along the edge, right, of our geometry. So if we go to our, in our previous example, we had talked about using the interior edge and naked edges, right? But that was for, the mesh boundaries. Now we're working with the mesh itself. So let's go to our mesh tools, and our naked vertices under Grasshopper 2. Be sure you're using the mesh that's been cleaned up and not the original. Otherwise, you'll have the naked points will be different than you expect. So, if we connect that here, you can see that the naked points are the ones that are on the boundaries of our geometry, right? Whereas the closed points are those on the inside, right? If I were to connect the original mesh to here, what you will find is that the naked boundaries are all over the place, right? Because none of those edges had been merged together yet, right? So that's just something to be aware of. So now that we've done that, you can see that we've already basically defined what our anchor points are, right? And they are going to be our points here, and insert that there. Oh, whoops. There we go. We also forgot to define factor length, so let's use a slider for that, as well as the strength, although it didn't make much difference in our previous example. Okay, if I hide everything from before, now you can see pretty clearly what it's doing, right? So again, depending on your length factor, you can adjust to see, how, tight a transition you want, or how, soft you want that transition to be. And if we wanted that, this curves to be smoother, we could up our UV count, right? And that would make those transitions less faceted and smoother. And that's, more or less it. We're only halfway there, right? Because if you look at our examples, all of these examples, they have also a round edge, right? And in our example so far, we still have this kind of squarish boundary from our original surface geometry and mesh, right? So to deal with that, actually, before we start, let's reduce this again first. To deal with that, what we need to do is we need to actually bring all those points in to form a circle, right? And the tricky thing about that is that, well, if we were to say, okay, let's use a circle component. So we go to curve in our primitive and we say circle fit, right? So we say, okay, I'm going to put those points in, and it's going to generate a circle that fits, those set of points. But the problem is that the structure of our data right now has all of these points, right, on a single list, basically, right? And if we, let's say we, grafted it, right? If we graft it, unfortunately, it creates 1 point per list instead of by sets, right? Which means that, unfortunately, that this component, the way that it was written, right, it doesn't allow you to kind of group, right, each of those naked edges separately. So to address that, what we need to do is we need to reorganize this data ourselves in such a way that we can change the grouping, right, of that data. And to do so, what we really need to do is we need to be able to figure out how many naked points there are, right, and how many openings we have, right, and then do the division, right? So we can do that using our list length, right? So we know that list has how many items? 48. And we know that we have 4 openings in our geometry, right? So we can use our math function, say divide 4, which is 12, right? And then we extract every 12 items and make it into a set, right? So we go to our sets, we say partition list, and we take our list of points, and we partition that list into sets of 12, right? So if we look at our list structure again now, you can see 1, 2, 3, 4, each with 12 items, right? And hopefully, when we draw those circles, you can see now that, okay, it's perfect. By dividing them, that original list, into 4 separate lists evenly, we're able to create that circle boundary, right? And writing it in this way, it doesn't matter, then how many points we create, right? A circle will still be fairly close to what we're expecting, right? So once we have that circle, though, the next thing that we need to think about is, well, how do we move our original points, right, from this square shape to our circle, right? And we do that by using a pull, right? So we can say curve and utility. Is it under vector? Should be under curve. Analysis. Curve closest point. Okay. So here we have the circle as our curve, right? And the point is the closest point to it, right? So you can see now that this point found the closest point on the curve. This point found the closest point on the curve. This point was here, and this point was there, and this point was there, and this point was there, right? So we've essentially replaced one set of points with a new set of points that are in the shape of a circle, right? So what can we do with that? Well, we can make this set of points our new target, right? Okay, but that doesn't work. And the reason it doesn't work is because I think here you can see we have a mismatch of data structure, the data hierarchy, right? this set we know is one list with a whole bunch of points, and this is now 4 lists with 12 points each, right? So I'm going to go ahead and flatten this first, and there we go. Now it's able to match those points up correctly. And you can see now, if I hide all of this previous stuff again, that now we also have round edge conditions, right? If we tighten this up a little bit and we now add more control points, we can get that to be really round and smooth, right? And the effect of that is, you know, let's go ahead and bake it out. The effect of that is that I am able to create geometry that follows the rules of minimal surface, right? To generate some of these types of shapes, right? Continue practicing some of these on your own time. And yeah, that's it. Okay. See you guys next week. Bye.